Solo mi amiga committee potente.
没有同意。
也是在这个我们是有分好的那个，你对，其他的这个好像可以中生哦，我是你讲了，先讲。你把什么
出来？怎么了？
我被抓，
什么意思？被打啊？
睡着了，不好说话，
不好说话。
就是嗓子很
哦
被逗。
，OK。可是他来上课又不跟他说话。
看到我就是想说，我在看你就
啊？OK
原来看到你有分享跟你分享的故事，
OK。
气死你！
是
就让人很想跟你交流。
是吗？有麦？没有麦。Hello，没有麦。
老板上课呢，
今晚没有什么？没有麦今晚。
没晚
麦，叫那个 technician 来。哎，Hello，mic is not working. Yeah, the mic is not working. Yeah，你有看吗？
没打好，然后我
没问题啊。
你给体谅一下。
我还有
他们有一点小，
相当，我等一下会给一点面。
我一做完就给小信。
他们需要。
我下午给他们的伙食还挺我吃很多，有这种要求。
Yeah，
有点太为难他们了。
看下怎样看，看他们做到怎样。
还有这个东西你想通了吗？
想通啊，它其实只有一个 variable 可以除掉。
对，就是这个意思。这才比较合理。
可是你可以选择性的。
哦，
我在对。
OK。是不准备加点。
什么？
你当时说你是不准备加点手机？
不是我不准备，就是我要先交几部分，
哎，我4年一起不交。
我可以丢到下一次哦。因为我要训练我的学生的那个知识量够先，我才可以上难度。不然的话上不了难度啊。
是看要跟别人交还是就看？
反正暂时他们是这样安排的，我也不知道他们讲，因为我现在目前我一直要讨的课是 GT， 还有另外一个门就不知道怎样安排。没有啦，我没有考那一轮啊。如果 compare GT 跟 NG 的话，我想教 GT 先，因为我要先把学生带上来，带上来过后我才进 NG 就比较做嘛。
如果下学期 A 级是别人教，你会想让我先学还是等你的课再学？
我觉得那个取决于你，那你是哪的话，我们可以做。没有事情，你按哪个加速分？全部都是我调的，很难讲，很难讲，很难讲。有建议，但是我不知道 因为是谁的场吗？谁的场吗？这个是他另外一个方向传出来，不是我们传过来发。
为什么那个是
不然你哪里是？他们从哪里进来？是那个评论是源自我们那天晚上。哦，
真的有这个？
可能不止你啦，我只是这样讲吧，应该是整个班里他的，
这个是你来。
不知道，不知道还没有安排。我只是考 GT 吧，没有办法，因为我想要把我学生带起来，没有办法，因为如果真空 GT 的话，我觉得更长。我这样我的前半段会白费的，就是我已经来带他们 MA，然后又带他们 Calculus 2，然后如果 GT 被人家标去，他们的知识会断层。
放你
对，也啊，那个还没有，我还不知道，还没有决定。Hello，他有做啊？有个晚上没？哦，哎，这样我们如果晚上上课有问题怎么办？不是没有人做啊？不够人，怎么不要请多一点人呢？请不到人啊？啊？OK，没有ABP 啊，因为我没有教过那个。哦哦，OK，对对对，可是他这个时候不是他自己打，他应该打电脑很快吧？我是不快啊，我上个学期打到我眼睛闪光，你知道吗？加深我 tutorial 2个 tutorial 都是我自己打的，hello testing， 可以调。hello，还在调整。
今天我们不上课。
OK 吧，OK 吧。
然后我们
OK，thank you 啊。
然后
Hello，
hello，
会比较好。后面仔，
影响上课。
这样比较好。还有是，对。
去这边。就学。
我发现现在专门
OK，这里边讲，这边讲，真的没有来。
被喷气了。
关东没。
悄悄下宝宝。
关掉开关。好。
过年。哎我。
好的。
他真的想念他。
让我上出轨吗？
精神出轨。
哦。卤肉饭，
卤肉饭哦，这边嘛，
你来。
那卤肉饭。一个问题。
对，肯定他本身对吧？他想可以。
比较好。OK， 啊，是远中。
那我们就下雨的时候上课。
海边上。
哦。
还是不要用这个。
给你特收。
不会了。关掉了。他关掉，他也是这样。哦，可能是因为他砸了，人家不要用。这样呢？这样，盖回去。这样。好了，雨下小一点。那又不要做这个东西。还是我们换房间？换房间。
可以。
啊？
有点浪费。
可以。看一下哪一个房间是空的。看房间哪一个？
这个 B110。
要换房间啊？啊？换吧。去检查一下。我去检查一下。隔壁那边101啊。
应该没有。你发了酒没有他来我们这。然后我可以摆这个，然后拖你过去。
下面这边有点封闭。
啊，隔壁有声音。
去隔壁哦。可以 post 一下那个 group， 我们穿去隔壁哦。post 在那个 group 下。
我觉得当时没人。
Testing，呀，这是他的，可以了吧？OK 啊，今天很多东西要 cover actually。Right. So before we start, we maybe we need to extend a bit tonight because I need to cover some content because we start late, right? Okay. The other thing is I want to give you hint on assignment 6 question 1. Okay, so very important hint, so please listen carefully. If you got any question, please ask now. Okay, so what's this question asking about? Let U, V be set of order 3. And then decompose U cross V into orbits. Okay, so there are two conditions, right? So when okay, so orbit of what? Orbit of the action or into orbit of the action, diagonal action. Diagonal action by x3. So how to define this diagonal action? So G in x3, G on UV, how to act? We act like GU, comma GV. Okay, so act the same way. Okay, act the same way. But there's condition, right? First condition is what? When the action of x3 on U and V are transitive. So this diagonal action here really depend on how you define your action on U and V by S3. Okay, maybe here is action 1, here is action 2. And then this G action on product set here is, maybe you can call it action 3. Okay, so does it make sense? Yeah, I mean, this UV should be a G set. Okay, so there's a G action on UV already. Okay, and then we want to take this action act on the product set. Okay, so here we have a G acting on U, and then G acting on V, and then this diagonal action here will have G acting on U cross V. Okay, so here is 1, here's 2, here's 3. Okay, so there are 3 actions here. Okay. So first condition is when U and V, the action of U and V are transitive. Second is where the action of S3 on U is transitive, but the action of S3 on V is what? Split into so split V into two orbit. So what are two orbit? So one orbit is just containing one element, the other one contain two elements here. Okay. So well, I mean, one action you can try is you let U and V to be the index set of indexes, and then you just add like a normal symmetric good elements. For example, how 1, 2 add on 1, it just sends 1 to 2. But you can do that case, but this case here, if you do that, okay, that is the one example of action, transitive action of S3 on U. Okay. So, I mean, let's write down what you will do first. For example, you let S3 acting on U equals to 1, 2, 3. Okay. And so the claim is this is, so the claim of this map is transitive. So add on this set transitively. Okay, I think this is what Albert did in the afternoon. So you let S3 add on this one set of 1, 2, 3, and then you figure out you figure out then you also set V equals to 1, 2, 3. Okay, and try and decompose. Okay, U cross V, in this case just 1, 2, 3 times 1, 2, 3. Get into orbit. Okay, in this case here, what you can see is your orbit is just an orbit of 1, 1 and orbit of, let's say, 2, 3. So what are inside this orbit? So first orbit, you will see all the tuples, okay, with repeated index. So let's say 2, 2, 1, 1, and 3, 3 is inside here. And then where the rest go? Okay, the rest will go into the orbit of, let's say, 2, 3 here. So what are the other things here? So you have 1, 2, 1, 3, and 3, 1, and then 2, 1, and then what else? 2, 3, and then 3, 2. Okay. Okay, so for these, you need to calculate yourself. Okay, I just give you direction. Go and compute it. Yeah, all of them. 3, 3, 9. Okay, so you should have 9 of them. So I'm already split now them into partition, orbit to partition our set. Okay, so we have 9 elements. So split into 2 sets. But in general, this question a bit tricky. This question says that it only say that the action is transitive. It didn't tell you what sort of action you do. Okay, so this is an example you should see how to answer the general question here. 哎，稍琪还在派啊？跟紧啊，先停先，等下下课再派。So how to do in general? Okay, so in general it's like this. So first step, you prove in assignment 3, right? S3 generated by what? S3 can be generated by what? Let's say 2 transposition. Which group presentation it corresponds to? It corresponds to the x1 square, x1, x2, such that x1 square equals to x2 square equals to identity, and then S1 and S2 will break. Correspond to this choice. Okay. So in this choice here, what kind of map I can do? I can send 1, 2, 1, 2, and then send x2 to 2, 3, for example. So what does this mean? This means that once I tell you, so let's say I want G to act on a U, okay? So how do I make this action here? As long as I tell you how these two act, all the other elements will get determined, correct or not? So for example, 1, 3. 1, 3, I can write it in terms of 1, 2, 2, 3, and 1, 2. How? It's just 2, 3, 1, 2, and 2, 3. Okay. So basically, I tell you how these two act. It already determines how all the other elements act. Because these two elements will generate by group. Okay. So what's the possibility of acting on U, which is order 3? How do you think about order 3 set? How do you think about it? Maybe one easy way to think about it is you can use apple, banana. Huh? Watermelon. 可能累，但是我喜欢吃。我喜欢的水果。Okay. Anyway, so maybe you can think of U as a set of any three elements. No need 1, 2, 3, right? Because the question just specify order 3. Okay. So you need to tell me how these transposition add on this set of 3 elements here. Okay, how to add on these 3 elements here? What are the way to act? So one possible way is they add like a identity. Okay or not? So let's say for all. So for all U in U, maybe they just act like a identity. Okay, L identity means what? Every element also act like a identity. So meaning the orbit is what? Orbit of every element is just itself. So meaning what? The action is not transitive. Okay, because you have not just one orbit. Transitive means what by definition? You only have one orbit. Okay, transitive means your orbit only have one. So first one is trivial action. It's not transitive. Second, how to think about it? What are the possible way to add on 3 elements here? 1, 2, and 2, 3. What are the possible way? What are the possible way? Or both 1, 2, and 2, 3 act non-trivially. Okay, both of them act non-trivially on U. But you need to think about it. What's the order of 1, 2, and 2, 3? Right, the order of 1, 2, and 2, 3 are both 2. Meaning what? You do once, you do twice, you have to go back to identity. What sort of action you can do? You do twice, 回去自己, go back to itself. Swapping, you can only do swap or transposition. Okay, so what can you do? Either you can swap apple with banana, or you swap banana with watermelon, or you swap watermelon with apple. Yeah, no. Okay, so since the order of 1, 2 is equals to the order of 2, 3, which is 2, they are non-trivial action on U must be transposition or swapping. Okay, why? As for example, 1, 2 on 1, 2 on U must be equals to E on U, which is U, and on the other hand, you also have 2, 3 on 2, 3 on U. Why? Because we are using the associativity law for group actions. Okay, associativity law. Then if you add twice, it equivalent to you just combine the group element, compose the group element. Associate DDP law. All right. So what could it be? What could it be? What kind of swapping you can define for 1, 2, and 2, 3? So there are two cases here, right? Case 1. So case 1, 1, 2, and 2, 3 do the same swapping. Case 2, 1, 2, and 2, 3 do different swapping. Okay. Let's say, for example, so I'll take another example here. Let's say 1, 2, and 2, 3 both swap apple and banana. What's the orbit of banana? What's the orbit of apple? What's the orbit of watermelon? What's the orbit of apple? What's the orbit of banana? What's the orbit for watermelon? Can you compute it? So you need to do actual computation. I always told my previous students, I'm an abstract person, but I'm practical at the same time. So I'm a practical abstract person. 懂什么意思？我是个务实的抽象派。通常务实的人就务实，抽象就抽象，又抽象又务实。所以我讲的理论是一定要可以写出来的，一定可以 work 出来的，完整的写出来的。对啊，我不是空讲的。OK， 我也不是白做的。我做的东西有理论的支撑，我的理论有我的行动来证实。OK 嘛？所以如果说这么难的东西我一定要写出来的。OK， 我要写出来。所以 orbit of apple 是什么 ？orbit of apple 是什么 ？In this case， well, I mean， 可能跟你讲两个，你还是看不是很清楚嘛，对不对？你可能应该要了解完所有的。You need to know how all elements act, right? What are the other elements? For example, 1, 2, 3. What else? So let's move S2. So what are the other elements in S3? Can you tell me? 1, 2, 3. 1, 3, 2. 1, 3. Okay, the other is identity. Identity is always there. So can you write these three elements as a product of 1, 2, 2, 3 or not? 小月来 try 一下。把这些 elements 写成 product of 1, 2跟2, 3。应该是 midterm 前的东西。把这个 disjoint cycle 写成 product of transposition。来给一个。知道我在问什么吗 ？OK， 是现在1、2、3。用1、2和2、3做出来吧。2、2、3，你是说这样吗 ？OK， 来，要不要 try 这边？1、3、2，刚才有没有一直比划了？来 try 一个。1、3、2，这样写成1、2跟2、3的 product。1、2、2、3，1、2、2、3，够吗？够。Okay, 1 to 2, 2 to 3. Okay, so 1 to 3. And then 3 to 2, 2 to 1, 1 to 2. So 3 to 2. And then 2 to 3, 3 to 2, 2 to 1. So you close with back. Okay, good. 1, 3. Just now I wrote it down already, right? 2, 3, 1, 2, 3. So if 1, 2, and 2, 3 both swap apple banana, what does 1, 2, 3 do? First, you sort apple and banana, and then you sort it back. So this is what? This action is what? Act like what? Identity. Okay, so this action is equals to identity. How should I write this? So if I apply this on you, this is equals to you. Okay, so okay, let's write this as act like an identity. How about 1, 3, 2? 1, 3, 2 should be the same, right? Because they are even transposition. Okay, even swap. Right or not? Yeah, apple become banana, become apple, become banana, become apple. Okay, go back to apple. Banana, banana become apple, banana, apple, banana. Don't go back banana, apple go to apple, banana go to banana. So act like an identity. Last one, you will become another swap. Okay or not? So you see under this action, what's the orbit of apple? Only got banana? Obviously got apple, right? Because identity add on apple should be apple. And then you will find that orbit of banana is the same as the orbit of apple. But watermelon is what? Just watermelon itself. So this will correspond to the where is it? The second type of action here. Split V into two orbit. Why? Because I can relabel my watermelon as V1 and then I relabel the other two as V1, V2, and V3. Okay or not? So what I want to say here is up to wait, gem. Okay. So what I want to say is up to reshuffling. Wait, how to spell shuffle? Shuffling. Okay, up to reshuffling. Reshuffling. Okay, up to reshuffling. We can name. We can label. Okay, we can label elements in U and V as U1, U2, U3, or you can label as V1, V2, V3. Okay, up to reshuffling, we can label elements in U and V as U1, U2, U3, and V1, V2, V3, such that 1, 2 really sends, IJ, okay, the transposition IJ really sends UI to UJ and IJ on VI equals to VJ. Okay, up to relabeling, we can just make it swap or transpose, okay, based on the subscript. Okay. 懂什么意思吗？刚才我们在交换水果嘛，对不对？但是我们可以 up to relabeling，就是你可以再重新给它标名字过后 ，then the transposition will based on the transposition, the swapping on the subscript. Okay, yeah, you can relabel such that your IJ will do this. For example, in our case here, let's say I say 1, 2 have to swap both apple and banana. So who should be U1, U2, or U3? So maybe you can let, in this case here, maybe you can let U1 to be banana, and then U2 to be, U1 to be apple, U2 to be banana, like that. Okay. Yeah. So that when you do the swap, you're really swapping the indexes. Okay. Okay. Any question? Up to labeling. Okay. Maybe use relabeling better. Relabeling. So case 2, if they are doing different swap, meaning what? You have two different transposition. So if you have two different transposition means what? You can generate the whole S3. Okay, you can generate the whole S3 already because S3 is just generated by two different transposition. So in this case, my claim is for case 2, the action is transitive. Okay, I think you should prove this. Okay, you should produce this proof. So I put proof here. So I say fill the hole. You should prove this. Okay. So if two transposition do different swapping, then it will be a transitive action. Okay. Okay. So if it is transitive, then this is what you want in this question here. So action on U and V are transitive. Okay. So I only told you how to get transitive action on a single set. So now you need to combine this action into the diagonal action and then look at the orbit. Okay. Understand? Yeah.
I don't think they.
You don't do, but
I
you
do, but I don't think they.
hey, don't look down on them.
I know. I
Maybe
don't
it's you.
look.
Don't look down on yourself. Yeah.
Maybe I'm not to you. I don't think you express this clearly to me.
Well, I mean, obviously, I want you to try, huh? Look down on me, yeah. Look down. So I mean, you can try first. We still got Thursday. Thursday still got time if you cannot figure out, huh?
We have more time.
No, we have last assignment to go. Cannot extend it. Yeah. Otherwise, not enough time. Okay, so try and study this hint, and then you can go and look around references, and then see what you can figure out. If you get stuck again, we can discuss on Thursday. Cannot, we still have time. I think the hardest one is this question. The others is kind of straightforward from definition. You agree with this? Okay, thank you. So the others is just definition, but this one a bit tricky. Okay, the tricky way is because we consider general action, which is transitive. It's not a specific one. But how to deal with general question? You need to start with a specific example and then see how you generalize it. Okay. So what I told you is how we generalize it. So we look at the action of transposition. Okay. Because I didn't fix any specific action. But what I claim is up to relabeling, the transposition is just what? Just swapping the element with the index. Okay, with a proper index. Okay, proper subscript here. Okay, up to relabeling. This is just what it is. Okay, nothing. Okay, how to relabeling is doing what it is always been doing. Okay, so out to relabeling, it is actually going back to the case of what Albert do in the afternoon. Yeah, out to relabeling. Okay, out to relabeling is just what you should think about this question. Okay, the general S3 action. Try and think about first. Okay, I like my student to think. I don't want let them to copy my answer. 有没有内涵？我是真的，我是这样的，我是这样。我以前还没有认识这个人的时候，我已经跟我学生讲，然后后来我发现原来这个人存在。我一直骂一个没有存在的人，后来被我发现这个人存在。我跟你讲，我理论是做到很厉害，我跟你说你啊，一个不存在的东西都可以把我挖出来。Anyway。 正经 I don't care。 OK OK 了。啊？静了今天。对，不要再激我，不要再讲了。以前啊，跟你们讲一个小故事。以前我很讨厌，不会讲到很讨厌的。就我第一届的那个学生的数学系学生，他们他们就讲，我只能说就是5个字吧，恨铁不成钢，恨铁不成钢，就是因为他们一直想要我教一种方式，就是给他这个题目，叫他这样做就好，他不想知道这题为什么这样做，为什么这样子解，他不会 stress， 你教他怎样解，他才 stress。为什么我要知道这些东西？我不要，我不要知道，我只要算吧。真的有这些人存在。你们是这些人吗？你们是这些人吗？我觉得你们，我不是讲你们不是这些人，但是你们，我不懂哎，我不懂怎样形容你们呢，其实，就是啊，什么？我不知道怎样形容你们，因为什么？爱是很难形容。
爱数学的话，那想
对啊，
所以你讲我啊？
说你只爱数学。
对啊，我爱数学。如果你爱数学，我就爱数学。对，但是如果你爱数学，我就爱你。你要transitive，说是transitive，所以我可以说他们不爱数学，或者他们不认识数学，或者他们所谓的数学跟我数学不一样。但是就是说，可能至少你们愿意去学哦。你们会不会骂我啊？其实会骂，OK 了。其实我也会骂我老师的，但是问题是我骂完我老师过后，不是我还是会去学，但是没有到有这样夸张。但是就是有一群人不是，他是骂完你过后，他要跟你做倒反，我就很讨厌，我很讨厌。因为为什么？因为我在做我的工啊。你是学生，你不学，你没有做你的工呢。You want to listen in English? Yeah. So it's not important for your academia. You just need to keep studying. That's all. Whatever I want to say here is for you to keep studying. That's all. Yeah. Don't learn non-stop. Learn non-stop. Learn non-stop because because I learned non-stop for 8 years. 8 years I learned non-stop. I think that I'm stupid in 8 years. I'm the most stupid one. I'm most stupid one. But after I came here, I realized that I'm not the most stupid one.
What the fuck？
我有营销咩？
有哎，他讲这8年我是感觉我最好。
Nothing. I don't want to say stupid, but just that I know something what people don't know. That's all. I know something what people don't know. Because I learn non-stop during the 8 years. Huh? But what I want to tell you is keep learning. Because you don't always met me. You don't always met me. 你不会参与到我。我只能这样讲。Okay, yeah. So make sure you dig everything you want from me. Yeah, dig everything you want before you leave my club. Okay. Okay. Yeah. So I just give you a hint. I'm not telling you any answer yet. So you still need to mix these two actions together, and then see what happens. So one, one important example you can do is like what? Is like what Albert do in the afternoon. No? Just take the normal action. Okay, normal U to be 1, 2, 3. And look at the orbit here. This will correspond to the transitive orbit. Okay, transitive one. And then I already tell you a gap, the bridge, how to go from general action, general transitive action to the specific one. Okay, up to relabeling, it is actually what Albert did in the afternoon. Okay, so you still need to figure out what's this specific transitive action. Okay, and then you can try case 2. Okay, combine case 2 and case 1 together. You're supposed to go and do research, but not copying. Okay, after understand, write down in your own. Okay, but if you rely too much, you need to reference. Okay, on the source, but you still cannot copy. So my way is like this. Even if I put an actual solution sheet in front of you, you also still cannot copy. This is how I train my student. 我把一个完整的答案放在你面前，都不可以抄。这样 rephrase. You need to learn rephrase. Learn to rephrase. Okay, this is very important because if you need to do FYP, thesis, what else, you need to write in your own way. Even if I put the 100%对的答案放在你面前呢 you still have to rephrase it. Okay? Yeah. So this is a skill. Rephrasing is a skill you need to learn. Okay, no? Yeah. Okay, man. Yeah. All right. Maybe we continue hint if you need on Thursday again. Okay, let you try first. Okay, so wow, 1:52. Huh? 什么？啊 ？No extent, yeah. 什么？今晚啊。今晚啊。So tonight we will class until 9 o'clock. Okay, 9 o'clock only I put you, let you go because we start late. That's right. Okay, so now let's take a break until 8 o'clock. Also cut short a bit. 8 o'clock start until full 1 hour. Okay. So let's start again on 8. So if you haven't get your cheat sheet, please come here and get it. Your cheat sheet. Wow. 厉害呀你！
你给我的病号
不太一样，因为我不要用这个方法讲。为什么？因为等下会很乱。
我是用你的那个方法写出来的。
对呀。
就他这个现在给我，我之前有一次问了他一个，我有点路，然后给了我的病号。
是一样的，讲一样的东西，只是不一样的方法。
Clarify 出来是一样的 ，Clarify 的过程不一样的。
对对对，这是什么 ？Classify。Clarify 是
long yes。
对什么？比较好的话语是什么？我讲不到。Clarify 是什么？看评。澄清。澄清。Classify。我有一个学生 define 跟 definite。因为 definition 嘛，它有那个
是 definition 不是 define 延伸过来的，
是，但是它 definition 也是有一个题嘛，对不对？所以它有一是 definite， 然后 sen，
好吧
，even RN。
OK。我的方法是相当于group action 对应到那个跟那个叫什么来着？我可能好难记。这个是推及 full S。
OK。Permutation representation。Permutation representation。
然后那个东西它是一个 homomorphic 的，所以它的 curve 必须是一个 normal 的 subgroup， 然后 S3 的 normal subgroup 只有 E、A3 和 S3。 然后你只要对这3种情况做讨论，其实它对它是完全这3种。
你自己想。
这不是你给我了 pink 吗？
是，我只告诉你科呢，我为什么？
对啊，我就是根据你这个东西，我后来想出来了，可以用那个东西来做出这个东西。
对，可以。宁静啊，要不要在？他们在。这么好的。可能决定谁要来 identity 吗？刚才我是在决定谁要来 identity， 你的全部那些 L identity 或者其中一个 L identity 或者都不 L identity， 因为其实这一个哦，其实这个对应和其中一个东西会 L identity， 就是这一个会 L identity，
两个还有一个。
因为它的 inverse 嘛就是 identity 啊，可是它跟它的 inverse 是这个。有名字，其他掉了。如果他们没有来就不要了。你要，
你这个文字怎么？你是口语。
要不然
刚才有一个免费的，来看，相片是这样啊，现在这个照片有，
他们认识好。哦，
一切是
他喜欢过来，他是常常会这样过来。然后都是几日不见，感觉你也认了不少。
还没有拍片呀，
人热的不少，你还没有
几个月啊？周末是
我要点，我要点。其实我觉得最难就难在开始，后面开那个我
是要走。红杰 here 吧。子航灯 ，OK。UG Jasmine。金鱼 ，OK。带一层。综艺版对吗？
好啊。
OK。下吧，我的人生，你们的人生，很抽象。金盆 ，OK 好。
就是你的一个东西怎么 act， 其实你可以把它考虑成是那个 M 级怎么 act。什么1/2还是什么的东西，就是那个排练的把那个 kernel 过来。就是最好。那个单词对不对？因为你对这个东西做开对话以后，你会发现就决定了其他的这个东西归档。
如果它可能是0的话，就是 transition external。
对。然后如果 kernel 是 S3的话，那就已经是 identity， 不是去别，不是 identity，
区别了，
就是去别。然后如果是 A3 的话，你就可以对它做讨论来，所以我们来区别的这个
这上面上面可以变到给它塞边。
刚刚上面不只有3个系配置，我的每一种配置其实会有这边的。
是一个 A3，
所以
A3 还是3个1？
哦 A3自己，
对，
这每一个都到不了。
对，因为 S3
一种啊，不是一个啊，一种。
对。
科呢
identity 是那个
没有了
transitive，
科呢科呢，
kernel 只有 identity， 那就没有其他东西 act like identity， 所以它不 transitive。
你只有1乘以每个东西。
对。
像 A3 的话有
A3 就会有 E2、E1，
就这个情况咯。
对，
就这2个 identity 咯 ，A3， 这个和 identity 啊，
它就会这样吧。
对，
它就会产生这个情况咯。
是啊，
两个
这2个东西 act like identity， 然后另外的3个就是一样。
哦，那这个 form A3 吗？
就是 on 可以哦。现在那个是 on。
对啊，这个是全部的的。
这个跟1223是一样的，这2个是一样的。
所以那个13不在 A3 里面。
13当然不在 A3 里面了。
Okay, we should start.
哦，我们正确要
可以，等下可以再讨论。Okay. So last time, before we end, right, we mentioned about you can do division of remainder with using one variable. In fact, you can do it with more variable. But how do we do it? Actually, a more precise statement for division with remainder for polynomial in 2 variable is like this. Okay, let's say you have 2 polynomial in 2 variable here. So what do you do? Assume that f is a monic polynomial of degree m when regarded as a polynomial in y. Okay, so meaning what? Okay, so what does it mean here? So wait, let me highlight. So what do I mean here? So seriously, I was regarding fxy is actually in rxy, right? R adjoint xy, but really we see it as R adjoint X adjoint Y here. Okay, so monic in Y means what? It is a unit in Rx. Okay, so the R, don't confuse you. This is just a random ring here. And then you can do this quotient here. So after this quotient, if the remainder is non-zero, then the degree, okay, in the variable y is less than m. Okay, let me give you an example here. Let me give you an example. So let's say we divide xy cubed plus x squared y squared plus x cubed y squared by this polynomial here, y squared plus x squared plus xy. So what kind of division I can do? Division in y or division in x? Okay, we can do division in y first. We can also do division in x, because if you regard this polynomial as r adjoint y adjoint x, it is still monic. Okay, it is still monic here. And then it is also monic if you regard it as r adjoint x adjoint y. What's the difference between these two? Do you know what's the difference between these two? So in this world, right? So in this world, how do we see x squared plus y squared plus x squared plus xy as a polynomial in y? So you really should treat x squared as a coefficient times a constant 1 polynomial. But how do you treat it as an element in r adjoint y adjoint x? So you should treat y squared as a coefficient of constant polynomial. Constant polynomial. Okay, so they are the same, right? Correct or not? High school tells you they are the same, right? You just commute. Okay, but we try to treat them in a different world. Okay, so how do you do division in R. So, sorry, how to do division in Y. So what do you do here? Go and find the highest degree Y first. Okay, try and cancel it out. How to cancel it out? You multiply xy to the f, okay, that you're trying to divide your function with. And then what's your remainder here? Did I miss out any remainder here? So xy square cancel. And then you produce 2 extra term here because you got 3 term. And then if you take x square minus y square, this will cancel also. Okay, so you're left with 2 terms here. S cubed y square minus s cubed y. Can you still do division? So the highest power here is y square. And the highest power you're trying to divide also y square. So you can do division again. So what to do here? You multiply by x cubed. Okay, so that you can cancel s cubed y square. And then you're left with 3 more terms here. Look at this remainder here. This polynomial has degree in y less than 2. Yes, right. The highest degree here is degree 1. Okay. So the other division you can try to do is with respect to x. Okay, you can do it with respect to x. So look at your polynomial that you're trying to divide here. The highest polynomial here is, in terms of x, is s cubed. So you can try and get rid of s cubed first. And then you find out that your remainder are all degree less than 2 in x. Right or not? Okay. Yeah. Okay. So in general, what you do, in general, you can single out one variable and then do division with remainder. That's all. Okay, that's what we want to say here. Okay. Yeah. Any question? 有问题吗？有问题啊，赵生。赵生狂点头。有问题吗？ OK 吗？ Any question? Yeah. So as long as it is monic in one variable, then you can try and do division with remainder. No matter how many variable include inside this polynomial. Okay. Yeah. Monic is very important. Mono. You have to always remember what is mono. What is mono? Yes, 1. Okay. So monic, you need to ask yourself what is 1 there. The leading coefficient is 1. Mono. Yeah. Mono. What word is come with mono? Mono. 要书写英文的有没有？啊 ？Second 什么来着？不要讲那个嘞，还有吗？应该还有其他 mono 吧？我知道，还有应该还有其他的 mono， 还有 mono 什么？代糖。单糖是什么？单糖。所以单糖的英文是什么 ？monosaccharide。呀，哎呦，应该还有英文字吧 ？Is there an English word start with mono 啊 ？Mono what? Monopoly. Mono. Oh yeah, monopoly. Monopoly. Why is it monopoly? Only one will become the monopoly. Poly by one person. I mean. Monodromy. OK， 好，可以，没问题。OK。两个呢？两个的英文字叫什么 ？Bi 也是 di 多另个 bicycle。OK，by yeah。三个呢 ？Tricycle。Yeah。So you need to be aware of these prefix. Prefix is very important. Okay. Okay, let's start new now. Okay, so this is a very important proposition here. So this proposition says that if you start with any ring, there is a unique homomorphism from Z to R. So let me ask you, what should this homomorphism should be here? If we are talking about two rings, it should be a what kind of homomorphism between rings? Z is ring, right? So what kind of homomorphism? How many type of homomorphism you learn? Group N. I forget already. Ring homomorphism. Ring homomorphism. I think you forgot already. Okay, so there is a unique ring homomorphism from Z to R. How to define? Do you remember what ring homomorphism have to satisfy? Rho phi of A plus B equals to phi A plus phi B, and then phi AB equals to phi A times phi B, and then one more, phi 1 equals to 1. Okay, I have to send multiplicative identity to multiplicative identity. So in this case here, how to define? We simply define phi n equals to 1 plus 1 plus 1 for all n greater equal to 0. And how about negative n? You just send to the inverse of phi n. Maybe you think it is stupid,白痴咩 ？n 送去 n 还要写1加1加 n 次。Stupid? Yeah. Yes. Why is it stupid? Because our ring can be different. For example, if our ring is a matrix, for example, our ring is a matrix. So let's say GLNR. Then what is 1 plus 1 plus 1 here? Then this is the identity matrix acting n times. Okay, so the one here is different if you work with different ring. So the one here is what? The multiplicative identity. Okay. Okay, so depend on what ring you have here. Okay or not? So it's not trivial. I cannot just put n like this. Because n might not make sense in every ring. Okay, might not make sense. Might not make sense. Might not be true. Okay. Might not be true that n live in any ring. Okay or not? Yeah. 懂讲吗？反正就是 n 不一定活在每一个 ring 里面。这个 matrix 你找到 n 吗？GLN 找到 n 吗？啊？对，这个是加 n 次，但是 n 就是 n 没有加 n 次，但是这个 make sense. Why this 1 plus 1 makes sense? Because every ring must has multiplicative identity. And then inside your ring, you must know how to add. That's all. Okay? 明白吗？来，放心，快，我们要加速你的 confusion. Stuck.
加两个不是变 n？
对，加了变 n，
又不是数字一。
但是你看在 GLN 里面，它就不是数字一了它是一个 matrix。Then in GLN 里面，它就是一个 n 层 identity matrix。Okay, 我写下来。So this is a multiplicative identity in R. So really depending on R. Okay, so it's really depending on okay, I really depend on R. Okay, I don't want to prove this. Go and prove yourself. Okay, prove that this define a homomorphism, and then prove that this is unique. Okay, unique. It is really fixed by this how you send n minus n. Basically, it's unique, right? Because I already tell you what all the n should go in that. Basically, it defines everything, right? Then what you need to check, you check It defines homomorphism, and then it is unique. Two things. Okay, so I don't want to prove, but you need to check that. The definition define a ring homomorphism and define uniquely. Okay, two things you need to check. Okay, so one thing homomorphism, two things uniquely. Two things to check. I want you to remember this result. I give you any ring, there's a unique homomorphism from Z to this ring. So Z is like a very basic ring. You have to know. Okay, there's a map from Z to R. So how to map? You just map N to N times of the multiplicative identity in that ring. And then negative N, for positive N, you did that. For negative N, naturally, by homomorphism, you should send it to the inverse of 5N. So you have a negative of 5N. Okay. Yeah. So I want you to remember integer is a basic ring. Okay. It has map into every ring, every other ring. Okay. So you can think of it. How do you think of it? So you have a Z. Okay. You have a ring R. You should think of it how this Z sit inside your R. So in every R, you have a copy of Z inside here. Okay. So you should think about Z like this. I give you any ring, you should be able to find a copy of Z sitting inside this ring. How to sit? Like what I told you, just have multiple of multiplicative identity inside it. And this is unique. This definition is unique. Okay, let's not prove this, but we want to go to kernel. Okay, so the kernel of ring homomorphism is interesting also. So let phi be a ring homomorphism between R and R prime. Okay, what's the kernel of phi? What do you think? These are all the elements in where? In the domain or in the codomain? In the domain that maps to 0. Okay, it's the same. It's the same as a group homomorphism. Okay, so these are all the things inside your domain that get sent to 0 under this map here. Similarly, what's the next thing you want to know about this kernel here? It will tell you about the injectivity of your homomorphism. It's the same proof. Okay, so a ring homomorphism is injective if and only if kernel of phi is equals to 0. Okay, go back and prove as a exercise. Yeah, so this is really similar to a group 1. Okay. To reader. Okay. Okay or not? Okay. So go back and prove this is similar to group homomorphism. Injectivity group homomorphism if and only if the kernel is 0. Contain 0 only. Or in this case, what do we call this this subset here? We call it a 0 ring. So in the group 1, we call it a trivial group. Okay, here is 0. All right. Okay. So it's very similar. There are a lot of repetitive between ring and groups. But now we're going to start a very new thing about ring only. Okay, only ring have this kind of property. So I want you to make one observation here. Well, you already know that kernel of phi should be closed under addition. So meaning if phi x equals 0, phi y equals 0, phi x plus y should be equals to 0. Also, phi xy also have to be 0 because phi xy equals to phi x times phi y. So curve phi here is closed under addition and multiplication. But there's one more very special things about this curve phi here. This is only ring homomorphism exhibited. So if X is in curve phi, then the claim is for every other ring elements here, if you take R times X, Rx will live in curve phi also. Okay, can you check it quickly? So let's do this proof here. So what is 5 of Rx? 5 Seng. What is 5 of Rx? 5R times 5X. But 5X is in the kernel. So no matter where 5R go, 5Rx should go to 0. Okay, so this is a very special property about the kernel of ring homomorphism here. If you multiply any ring homomorphism to X, and X is live inside a kernel, then Rx will live inside the kernel also. So this, so I want to make an option here. So this property abstract it into a concept that we call an ideal. Okay, abstract it. Ideal. What do you mean by ideal? 理想 I think 华语的教材也是把它翻成理想。So let me try and write history here. What did I find here? So 为什么它叫理想呢？ So actually, this would come from that they want to uniquely factor every element in a ring. Okay, so they want to factor. Wait, 这个 AI 就跑出来。Okay, so they want to factor every element inside a ring. Okay, I mean the ring they consider in algebraic number theory. So what do I mean by uniquely factor every element in a ring? This is like you should think about how integer can be written as a product of prime unit. Okay, yeah. Okay or no? Yeah, you should think about why our integer can split into product of prime number. This is the prime factorization theorem, right? So they want to do it in a random ring. Also, they want to do it. So how they do it? They need to use this ideal. I think in our course we barely touch this unless you go to A2 or you go to algebra number 3. You will see how they use this ideal to split up numbers. Okay. So they want to, their dream is to factors elements. Right. So let's define ideal now. So what is an ideal? So an ideal of a ring R is a non-empty subset of R with the following property. So what's the property I want to say here? I is closed under addition. It's like a subgroup. Okay, closed under addition, but more than a subgroup. So what's more than a subgroup here? The second property is if, okay, X is in I and R is in R, then R times X is in I. Okay, so a prototype of ideal is the kernel of ring homomorphism here. So what's the relation between this and what you learn in group theory? Kernel of a group homomorphism, you corresponds to what kind of subgroup? Normal subgroup. Okay, so here the kernel of a ring homomorphism corresponds to ideal. Okay, yeah. So ideal. Right. I think I just skipped the remark. So for example, let's give an example here. So example of ideal, or the claim is the set of multiple of 2. So let's say the set 2Z forms an ideal in Z. Okay, how do you prove this? How to prove? Two things to prove. Is it closed under addition? Okay, so let's say 2m plus 2n. Is it still multiple of 2 or not? 2 times m plus n. Second, if I take any, okay, element, let's say p in z, is p times 2m still a multiple of 2 or not? Because integer commute. Okay. 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 So even number form an ideal in Z. Any question so far? 有问题吗? So remember again, last time we learned subgroup, right? How do we build subgroup, right? We use generator. Okay, in this case also, we also can use generators here. So let's look at the first definition. In any ring R, so we can look at the multiples of a particular element A, for example. So let's look at a particular element A. And we said that this element form an ideal. Okay. So how do you think about the element inside this ideal? A plus A, right? Because close under addition. And then multiple of A, R times A, okay, will live inside this ideal. So this ideal we'll call what? We'll call the principal ideal. Okay, principal ideal. Principal ideal generated by A. So how do we denote this? So let's denote this. So how do we denote it? Either we can write angle bracket A or round bracket A or A times R, which is really equals to R times A because our ring is commutative. And what exactly is this? These are all the little R times A such that R is in R. Okay, so let's do a quick proof of this. It's an ideal here. Okay, so prove that we really define an ideal so that I can refresh your ideal definition also. So first of all, how to prove that this is an ideal? Well, we really start with a non-empty subset here. Need to be careful. So we don't call the empty set an ideal. Empty set. Okay. So why is it non-empty here? So this is non-empty because 什么来反省 ？A 为什么在里面？A 为什么在里面？差一点点。Why A is inside here based on this definition here? A times the multiplicative identity, good. Because multiplicative identity exists. We are not considering zero ring. Okay, second, close under multiplication. Addition first or multiplication? Which one do you want to do first? Addition. Okay, let's do addition. So close under addition. So you need to ask yourself. So ask yourself for every R1, R2 in R. So why R1A plus R2A is in R? Why? So you need to write in the form of a ring element times A. So how do you write it out? What do you do? Oh, sorry, in AR, thank you. Let's say this bracket. Okay. Factor. Factor what? 你现在要比较 professional 一点嘛？你都大学了。Factor 在大学我们叫 distribute. Okay, so we need to distribute it. So how do we distribute it? So R1 plus R2 times A. But we know that ring is closed under addition. So R1 plus R2 is an element in R. Okay. Okay, good. So this one closed under addition. Should we close under multiplication or not? No need to check. Why I check? Weird. Oh, I want to show that it is a subset. Okay, so we show that it's non-empty, right? We forget to show it is a subset. So here is about non-empty. Here is non-empty. So why is it a subset? Huh? Subset. So what do you need to show for subset? This principal ideal live inside R. Why is it a subset of R? Why? What's the definition of principal ideal here? All the ring elements times A. Okay. R come from where? Ring. A also come from ring. So you multiply two ring elements, it should be live inside R. So because R is closed under multiplication. So we have a non-empty subset now. It is closed under addition. One more thing to show is if you take any R in R, and any X in the ideal, I want to show that R times X is living inside the ideal also. Okay. So is it obvious or not? Huh? Is it obvious? Take R in R, X in A, then X equals to R1A for sum, R1 in R, then after, so R times X is just R1, R times R1 times A, and then because it is associativity, so you can prove R1, R times R1 times A, and then this is in the ideal of A, Y, greater by, because R is closed under multiplication. Okay, yeah. Yeah. Okay, not following. Okay, got question? So what are the example of principal ideal? So let me give an example. So for example, just now I show you that 2Z is an ideal in Z, but actually this is a principal ideal. Okay, you can use 2 to generate. Like the group, right? If you are looking as a subgroup, the subgroup of even number also generated by 2. Okay, so it's the same, similar reason here. Later I will later I will show you how to show generation by how to show ideal generated by some elements. Okay, I will show you later. Now I just give you a flavor first. Okay, what are the principal ideal? So actually, you also can use a -2 to generate this ideal also. Think about it. Can you use a -2 to generate even number or not? Can you make 2 out of -2? 来，冰下。Can you make 2 out of -2 in the ideal? 听得懂我问什么吗 ？OK， 很好，非常好。来，可以用减2来做出2吗？在 ideal 怎么做？所以可以大声一点吗？可以。啊，能吗？先回答能还是不能？ 能 OK， 如果能的话怎么做？怎么做 ？How to produce 2 from -2 in an ideal? What are the valid operation you can take in ideal? You can add, you can take product with the ring element. Okay, so how do you produce 2 from -2? 中一方面可以帮他一下，怎么造2从减2？在 ideal 里面，减2怎么变2呢？我问你一个问题。假设 ring 也不认识，我问你，怎样从减2造出2？只可以用乘法，对不对？假设啦，用乘法，减2乘什么乘以2？什么？负1？负1啊？确定一点，确定一点，确定一点，减2乘减1是不是等于2？是的，肯定的，肯定的。哎，如果这个题目都迟疑了，就很难 prove 东西了。这个是肯定的，减2乘减1是2，但是 you need to ask yourself 啊 ，is -1 inside the ring we consider or not? If is -1 live inside that? Yes, right. Okay, so you can take -1 and -2, you can produce 2. Okay. Okay. So another example I want to give is a non-example. So what's a non-example here? I want to consider an ideal in a ZX. Okay, so it's a polynomial ring over Z containing 2 and X is not principal. Later we will see. But I want to give you a flavor first. Why? Why is it not principal here? Because you cannot make 2 out of X and you also cannot make X out of 2. Okay, because they are linearly independent over Z. When I say make, you need to ask yourself, what sort of scalar you are considering? So now it's over Z. Okay, so you need to ask yourself, if it is over ZX, then it's a different story. But if it's over Z, then you cannot make 2 out of X or X out of 2. Correct or not? Because you need to ask the question, if AX equals to, 2A plus XB equals 0, so you need to ask yourself, does it exist any AB in Z or not? Okay, such that so you need to ask your question whether there exists a AB in Z such that 2X plus SP equals 0. Okay, if no, then they are linearly independent. Well, I mean, you need to get rid of 0 because always you will get A times 0 plus X times 0 to be 0, right? But we want to exclude this case here. Okay, any question? 有问题吗？如果听不懂啊，你一定要问啊，因为我讲的东西是很清楚的，所以如果你觉得还清楚一点 ，OK 吗？呀，因为我讲的话就是要给人听的 ，OK， 我讲出来的话不是留在空气飘走的，所以你要听清楚。Okay, so let's continue if you don't have question. Next proposition. Well, what's the obvious principal ideal here? The claim is the ring itself is a principal ideal. Okay. So what do you think? What is the element that generates a ring? 我说它是有一个东西 generate 出来的，你觉得是什么呢？来 Lydia. Hey, which identity? Which identity? Got 2, right? Additive identity and multiplicative identity. Which identity? Yeah, multiplicative, right? Because R times identity, you will get R. So you can get everything from 1. And this ideal has a special name. This is what we call the unique ideal. Okay, unique ideal. Because 1 is invertible. 1 is unique. Okay, do you know how to prove this? How to prove this? Actually, by definition only. So what's the definition? What is the ideal generated by 1? R times 1 for all the R in R. But what is this? This is just R. Okay. So R is an ideal. Okay, R itself is a principal ideal here. Okay, so what do you think? What's the next ideal I can introduce to you? So now it's multiplicative identity, right? So you also can build an ideal using additive identity. So in that case, what do we call it? Trivial. Yeah, zero ideal. So the principal ideal generated by 0 is the zero ideal. So how many things inside this zero ideal? What do you think? Nothing. You think. 零 something Ling is something nothing is empty. Okay, nothing is empty. 把这个不是0块钱这个有东西。OK， 所以这个真的有东西这个是 additive identity In mathematics nothing is empty set. Okay. So by definition, what is ideal generated by 0? Every R times 0. So you just get the additive identity here. So in these two cases, you can easily see that easily see what? See it forms an ideal. Okay. But actually, from what we prove for general principal ideal, they already form ideal also. Because in the proposition for general principal ideal, right, we don't care what is A. Okay, we don't care what is A. But here, we choose A to be 1, we'll get everything. Choose A to be 0, we get 0. Just 0. There we just get 0. Okay. Very straightforward, Okay, next. So we'll call that an ideal is proper, like a proper subgroup. Okay. Ideal is proper if it is neither the zero ideal or the unique ideal. Okay, so we can use ideal to phrase this proper ideal here. Okay. Let me ask you a question. Is ideal a subring or not? Is ideal a subring? Is ideal a ring? Yes? Yes. No. No. Why not? Yeah, 1 might not be inside there. If 1 is inside there means what? It is the unique ideal. You get the whole ring. Okay, so this is a very important remark why we want to study ideal. An ideal is actually almost a ring already. Okay, it's almost a ring. But except what? Except 1 might not be in I. Because if you can find 1 in I, that means what? You can generate the whole ring. Okay, so you will generate the whole ring. Okay, no. Okay. Okay, so let's try some exercise. This exercise is quite important for your assignment 7. Let's try and do it. So let's look at some ring homomorphism from Rx to R. This map here will fix R. So last time I told you that I need to have a ring homomorphism from the coefficient ring to codomain, right? So in this case here, it means that the coefficient will send to R, it's fixing R. But I still need to tell you where X go, okay? Come on. So in this case here, I send X to 2. So this is an evaluation homomorphism. Evaluation homomorphism. Okay? And so I claim that once I tell you this, this will extend to a ring homomorphism. Okay, this will extend to a ring homomorphism. So what's the claim here? What's the kernel? What do you think? What is living inside the kernel here? Okay, I put a claim. What's inside the kernel of phi? The kernel of phi is something in the domain, right? So what things in the domain will evaluate to 0? 0, obviously. Okay, good. Because 0 always goes to 0. Other things, based on this map here, what will go to 0? What polynomial will send to 0? Sends to 2, right? So how do you make 2 into 0? 减2, good. So where should you put the minus 2 then? X minus 2, good. Okay, so actually you found that X minus 2 is inside this kernel. But my claim is the kernel here is generated by X minus 2. It's a principal ideal generated by X minus 2. Okay, so let's prove it. Okay, we have to prove it. Prove this claim. So to prove this claim, this is a equality of set. So you need to show two directional. So which direction is easy? What do you think? Left to right or right to left? Right to left, right? Okay, because we know that. So let's do right to left first. So it's this one. So this one is easy. Why is it easy? Because everything in the principal ideal of X minus 2 is what? All the ring elements times X minus 2 such that the elements live inside Rx here. Okay, so you need to show that phi of R times X minus 2 is 0. Okay, but what? But for every R in Rx, okay, or I fix real R, okay, then good. For Rx, phi of R times X minus 2 is what? Because phi is a ring homomorphism, I can simply write phi R on phi X minus 2. But why phi X minus 2 is 0? Because we can split it further. Phi X minus phi 2. Okay, but phi X we send it to 2. And then phi will fix real number. So it's just 2. So you get 0. But there's a subtlety here. What's the subtlety here? R is a polynomial ring of Rx. R is living in a polynomial ring of Rx. So in general, what? This R is a finite sum of finite linear combination of more powers in different monomial. Okay, so in general, it is like this. So let's say like this. Okay, in general, it's this. But we don't care. We don't care. Because as long as it is multiplied with 1, 0, everything will go to 0. Okay, now in principle, this might be very complicated. And then the image also might not be 0. But who cares? Yeah, because this non-zero element will always multiply by a 0 element. Yeah, not. All right. How about the other direction? What do you think? The other direction, what do you need to show? For every elements in the kernel of 5, you need to show that it is generated by x minus 2. You can write as a multiple of x minus 2. Meaning what? Multiple of x minus 2. Meaning everything inside the kernel can be divisible by x minus 2. Okay, so let's do this argument here. So we will show this by division with remainder. So what to do? So let's take any polynomial x in curve phi. Okay, so we're gonna do division with remainder in Rx. We can do it, right? Because this is just one variable. We can even do it multiple variable as long as you pick one variable out. So if we do this, what happens? Px will be equal to some quotient polynomial times x minus 2 plus Rx. Okay. But what's the degree of Rx? What's the degree of Rx here? 你剩下来的余数一定要比较小，对不对？ So the degree of Rx must be less than the degree of x minus 2. But, right, correct. So x minus 2 has degree 1, right? So Rx has to be degree 0. Okay, since the degree. 哎，你们不要这样写啊，不要这样写啊，不要这样写，知道为什么不要这样写？啊？哦，上次你们是写在 order 上面哈 ，order 不要这样写啊 ，order of an element 不要这样写 ，order，知道我讲什么吗 ？order of x 不要这样写 ，don't write like this 啊 ，order of x 啊 ，don't write modulus。I know that a modulus of a set is like this, order of a set. Okay, that next. But for element, don't write like this. I still see people writing like this. I will take off marks. Okay, so don't write like this. Don't confuse. Because we define the absolute of an element in 3 group also. We count the length. So we don't do this for element anymore. Okay, so don't confuse yourself. 懂我讲什么吗？然后大家知道我讲什么吗 ？Order of an element 不要用 absolute value， 因为 absolute value 我们 define 在 free group 里面，也是给 element 的，但是我去算它的长度，也不是 order。Okay, so here we have a degree of Rx strictly less than the degree of minus 2. But what's the degree of x minus 2 here? So it is 1. So it implies that the degree of Rx should be 0. Okay, it should be 0. So R has to be constant. Okay, R has to be constant. But what? But phi of Px is equal to what? Px comes from where? Kernel of phi. So this thing should be 0. Implies what? Phi of the right hand side also have to be 0. Okay, but if you split out the right hand side, what do you get? Phi of Qx times x minus 2 by ring homomorphism, you get that this is adding with phi of Rx. But you know that x minus 2 also live in the kernel, so this term goes to 0. So you just live with phi of Rx. So R is a constant. What constant has to be? 0. Can it be other constant or not? Can it be non-zero? Why? We said that phi will send constant to constant. So this implies that R equal to 0. So if R equals 0 means what? S minus 2 will divide x. Because remainder is 0. 对吧？如果你除到后面余数是零，代表什么？它们可以被等除。OK. Any question? Any question? Okay. Straightforward. Okay, 5 more minutes. 5 more minutes. Let me try. 其实不离很远。Okay, 5 more minutes. Let me give you some other example. Let you go back and do. So next, if you look at another ring homomorphism, so now we upgrade a bit. We go from 2 variable polynomial to 1 variable polynomial, also fixing R. What is this? We will send x to t squared and then y to t cubed. Okay. Want to guess what's the kernel? Want to guess what's the kernel? Yeah, what's inside this kernel? Before showing they are equal, right? Guess what is inside there first. Ling is always there. No need to say what. We always send ling to ling. Okay, but what's a non-trivial? Any non-trivial polynomial gets sent to ling. 不知道，老师不知道啊？没有，你讲没有 ？You sure? Play around with t. 这个 example 是从 calculus 来的。Yeah, so if you try x to the power cube minus y to the power square, you should get t to the power 6 minus t to the power 6 under this homomorphism. So the claim is this is a principal ideal generated by this polynomial. Yes. So prove it, left to right, right to left. Okay. So which direction is easy? Right to left. Left to right, again, try division with remainder. Okay. Try division with remainder. So in this case here, a bit complicated because 2 variables. Then maybe you need to do it 2 times. If I'm not wrong. But I'll provide you answer. You go and try first. Okay. Let's see what else I can do. Yeah, I can keep continue first. So this one left as a homework. You must do. Go back and do. Left as homework. 老师会出差不多一样。怎么你不信我没？那就不信呗。OK。我靠。OK。问题是公单没有做完。What time is it? OK， 还有2分钟，我觉得我不要再写了，我觉得浪费时间。哎，但是我们要继续读。OK， so let's quickly go through some kind of repetitive. Every time we describe for one variable, we will do it for multiple variables. So let's look at this one. So just now it's principal ID, right? So now let's generate by a few elements here. Okay, let's say the ID is generated by A1 up to AN. Okay, inside the ring. And what's this ID here? This is the smallest ideal that contains this element. So what does it mean? So you just take any linear combination of A1 up to AN. Then they will form an ideal. Prove it. Okay? Prove that the linear combination of A1 up to AN over a ring, okay, in a condition, form an ideal. Okay? Prove that this form an ideal. Go back and prove. Why is it non-zero? Why is it subset? Why is it closed under addition? Why is it closed under multiplication? Can you quickly see or not? Why is it closed under addition? If you take 2 such linear combinations, add them together, is it still a linear combination? A1 up to A. And then if you take multiplication by a ring element, does it still look like this or not? R times everything. You can distribute. So you can R1, R2, R3, R until R. Okay, still look like this form. Okay, so it's an ideal. And then next example is this. So if you look at this Ring homomorphism here. Do you understand this ring homomorphism? If you take a polynomial in Zx, so what do? You evaluate it. You substitute x equal to 0, and then mod p. Okay 了 ？Sorry， I mean 就选一种哦，你可以考虑其他种。And then the claim is the kernel of this homomorphism is P and X. If you before proving it, is it clear about P and X live inside this kernel? Is it clear? P mod P 0. X mod P, X sends to FP is what? Go to 0. 0 mod P is 0. And so the claim is P and X will generate this ideal here. Okay, P and X is enough to generate the ideal, the kernel of this homomorphism. You need to prove it up. Okay, so what time is it? Okay, 2 点了。韩星很赶着回家。So okay next time we start with this example. Okay, next time we start with this example. So see you on the Thursday. 喂，我上个星期很准时，好不好？
赶着回家。
对，拜拜。
那我睡一点，我睡着。
有一点点。对，我看到你爬起来，很快。
为什么是 F0？
XR 呢 ？XR 丢上去2mod P。哦。我还给那个 X 有一个